This is lesson 7.2, equilibrium position and Kc. So the position of equilibrium, which we symbolize Kc, is a fixed value for a particular reaction at a specific temperature. So every reaction has a Kc for each temperature. So every reaction has its own Kc, and if this is our reaction, so AA, little a being the coefficient, big A being the chemical, plus BB goes to CC plus DD, then in order to write Kc, what we would do is put the products, and you can see that it is each chemical, C and D, raised to the coefficient, so little c, little d, over the reactants. So big A, big B, raised to the little a, little b, the coefficients. So here's an example. Write the equilibrium constant expression for the following reactions. So A, problem A, 2NO plus O2 goes to 2NO2. So we can see that the product is NO2, so we write Kc equals the concentration of NO2, and the coefficient is 2, so squared, over the reactants, NO squared, because the coefficient is 2, times concentration of O2. For part B, we can see that the products are this long molecule, so Kc equals concentration of CH3, COO, C3H7, there's no coefficient, times the concentration of H2O, all over the concentration of CH3COOH, acetic acid, times the concentration of C3H7OH, which is propanol. Here's another example. This time we're going to write the equations for the reactions represented by the following equilibrium constant expressions. So number 1, Kc equals NO2 squared over N2O. So we know the products must be 2NO2 and the reactants must be N2O. So N2O goes to, remember equilibrium has a double-headed arrow or two half arrows, 2NO2. For the second one, we can see products over reactants. So the reactants are going to be methane, CH4, plus water, H2O, in equilibrium with carbon monoxide plus 3 hydrogen molecules. So what can Kc tell us? Well, the magnitude of Kc is really important. If Kc is greater than 1, that means that the reaction lies to the right and that there's more products than reactants, even though it's still at equilibrium. If Kc is less than 1, the reactants lie to the left. The reaction lies to the left, meaning that there's more reactants than products, even though, again, the system is still at equilibrium. When K is greater than 1, right, the numerator must be greater than the denominator. So since Kc is products over reactants, products must be greater than reactants. When Kc is less than 1, the numerator must be smaller, so the products must be smaller than the denominator, the reactants. So there must be more reactants, it lies to the left. So why is this important? Well, Le Chatelier's principle says that a system at equilibrium, when subjected to a change, will respond in such a way as to minimize the effect of the change. So what does this mean? Well, the first thing we can do to shift a reaction towards the products or the reactants is to change the concentration. So if we change the concentration of reactants or products, the reaction is going to shift in order to use up the excess concentration. Kc will not change. The number will stay the same. We can change the pressure. If we increase the pressure, we are going to shift the reaction to the side that has less moles of gas. If we decrease the pressure, we'll shift to the side that has more moles of gas. Again, this does not change the value for Kc. The third way that we can shift a reaction is to change the temperature. When we change the temperature, the reaction is going to shift to consume excess energy or make more energy. So if it's endothermic reaction, meaning the energy is going into the reaction, then the reaction is going to shift to the right. If it is an exothermic reaction, meaning the energy is at the end, then the reaction is going to shift to the left. And this is a situation where Kc will change. For endothermic reactions, Kc will increase. For exothermic, it will decrease. And we'll do an example of this in a second. The fourth way you can shift a reaction is to add a catalyst. Catalyst will not affect the position of equilibrium or Kc, but the reaction will come to equilibrium faster. So why is this important? Well, in industry, there's many applications where they want to maximize the yield of a process. So not only is Le Chatelier important, but kinetics is also important, because you want to make sure that in industry you're making your substance, whatever it is you're selling, quickly. So here's an example. The Haber process is the reaction that's used to make ammonia. So nitrogen plus 3 hydrogen goes to 2 ammonia. This ammonia is used in a variety of ways, most of which is used for fertilizer to grow our food, but it's also used to make plastics like nylon, refrigerants, and explosives. So how could you optimize this reaction? Well, there's a few things to consider. The first thing we could do is increase the concentration. If we add more reactants, it will shift to relieve that stress, so it will shift to the right, making more products. The other thing that you could do is increase the pressure, because we see on the left side we have 1 plus 3 moles of gas is 4 moles of gas, and over here we only have 2 moles of gas. So if you increase the pressure, you'll shift to the right, the side with less moles of gas, and you should be writing these examples down. The next thing that you could do would be to decrease the temperature. So if you decrease the temperature, this is an exothermic reaction, so heat is on this side, it's a product. If you decrease the temperature, the reaction will shift to make more product. Okay? And the last thing you could do is add a catalyst to make it go faster. Another example of an industrial application is the contact process, and you do need to know these for the IB exam. The contact process makes sulfuric acid. Okay? Sulfuric acid is the most used, or the most made chemical in the world. It's used to make fertilizers, detergents, dyes, explosives, drugs, plastics. And the contact process occurs in a few steps. So the first step is reaction 1, and this is when they just take solid sulfur, which is yellow, and they combust it. So they add oxygen, burn it to make SO2. In reaction 2, they need to oxidize that SO2 from the first step by adding more oxygen to make SO3. And this is the rate determining step. This is the slow step in this process. And you can see it's very exothermic. The third part of making sulfuric acid is the combination of SO3 with water, first absorbing into sulfuric acid and then reacting with the water. So SO3 reacts with sulfuric acid to make H2S2O7 plus water, which then sets up an equilibrium to form more sulfuric acid. So for this particular process, in order to increase the efficiency, you would focus on step number 2, because reaction number 1 and reaction number 3 are very quick steps. Now, reaction number 2 is the slow step. So if you use Le Chatelier's principle to affect step number 2, you will increase the efficiency of making sulfuric acid.